Okay, so now we will see what are the various equations which are involved in resonators. So here you can see we start with, like for TM mode, we Ez is a function of, if we can express function of three variables x, y, z, each dependent on x, y, and that z only. This is variable separated all. So here xx can be written x, y, and zx. All three can be written in this general form. Now kr square, one quantity can be defined by relating a, b, and c. A, B, and C, A square, C square, and this equation can be defined where Br is for resonator. What is the propagation constant? So Br square, where A, B, and C again can be the same line of logic as the waveguide. When M and L, all this time one L factor is also coming, which is 0, 1, 2, 3, and so on. Here we have three boundary conditions to solve. Obviously it is closed on all sides, so three boundary conditions. So Ex, Ez, like Ez is 0 at x0 and xa, if you see that diagram, Ez is 0 at y0, yb, Ex is 0, Ey is 0 at z equals to 0 and z equals to L, means the opposite sides, which is closing that rectangular waveguide. So after simplification you should get it in this form. Here we are not showing in details because line of logic is same process. So in this way you get one FR, which FR is not cutoff frequency here. Here the concept is of resonating frequency. So from here, if you know the dimensions, if you know the M, N, L, and if you know the broad ball, narrow ball, and the other dimensions, then from here you can find out the resonating frequency, and from there you obviously you can find out the resonating wavelength. And for TA and for TE mode, Ez is equals to 0, as in the case of TM mode, Hz is expressed in this way. So like this for TE mode also it can be expressed in this way. Okay, so here like for TM mode Ez is 0, and in case of TM mode Hz is expressed in this form. Now we can find out the equations for Hz in a similar process. So you see the process is the same, only have to remember which component to equate what. So that only we were doing. So here using boundary condition again we can do the following simplification. So here again dominant mode is defined as the mode which has the lowest resonant frequency for a given cavity size. Here lowest resonant frequency Fr. So that which is lowest, that is the dominant mode. The waves are represented by T, M, and L. You see one extra parameter has come, L. Now degenerate mode is what? Modes having same resonant frequency are called degenerate modes. Two modes having same resonant frequency we can have if all other parameters are same. Ideally the walls of resonant cavity have infinite conductivity, but practically the cavity walls may have finite conductivity because no conductor is perfect. So as a result some stored energy is lost as ohmic loss in that imperfect conductor. So in the next class we will do the quality factor, because whenever we talk of resonator, Q factor plays a very important role, which gives an idea about the bandwidth, center frequency, and also the loss.